Hello everyone, and welcome to a multi-technique characterization of fuel cell and lithium-ion battery materials for QC and R&D. I'm Matt Thorne of LabRoots, and I'll be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by Horiba. To learn more about our sponsor, please visit horiba.com. We do encourage you to participate by submitting your questions you have during the presentation. To do so, you can simply type them into the Ask a Question box and click Send, and we'll try to get to as many questions as we have time for at the end of the presentation. You can also submit any technical issues there as well if you're having trouble seeing or hearing the presentation. I'd now like to welcome our two speakers, Sergey Mamedov, application scientist at Horiba, and Kayvon Savadkouei, application scientist also at Horiba. For a complete biography on our speakers, you can click on that biography window on the left side of your screen. And Kayvon, I'll go ahead and pass it over to you, and you can begin your presentation.
Hello, everyone, and thank you, Matt, for introduction. Before I go to our main topic, which is introducing different analytical techniques for characterization, quality control, and reverse engineering of components of batteries and fuel cells, I want to briefly talk about battery and fuel cell technologies. So lithium-ion battery and fuel cells are two promising technologies which can help us to achieve our goals in reducing carbon footprint in transportation sector. A fuel cell is literally a small power plant which uses hydrogen as clean fuel to produce electricity. The byproduct here is water. The structure of fuel cell is complicated, but here we simply focus on three components: electrodes, which are responsible for transferring electrons; catalyst, which is responsible for generating hydrogen ions or oxidation reaction; and electrolyte, which is responsible for transferring ions in the cell. The electrolyte or catalyst, which we use in fuel cell, defines the type, application, operation temperature, fuel type in fuel cell batteries. So compared to fuel cell, the lithium-ion batteries are power storages, which can store electricity, and they can be recharged after using the stored electricity. We normally store electricity in form of lithium oxides, and when we use this electricity, we can convert lithium to lithium oxide in recharging cycle. So each lithium-ion battery is made of anode, which is mainly lithium metal; cathode, which is an oxide form of lithium; electrolyte, which transfers ions; and the separator, which keeps the two sides of the battery electrically separated. Depending on the type of oxide of lithium, the lithium-ion batteries are categorized, and you can see some examples here in this slide. Now, let me, I think there is a delay here, sorry. Okay, so let me introduce the GD Profiler 2, which is one of the elemental analysis techniques that we introduce here and we use for lithium-ion battery and fuel cell characterization. This instrument can analyze the elemental composition of sample layer by layer from the surface. So basically, the information that we receive from this technique is the depth profile of the sample. So let me explain how I moved fast. Sorry. So let me explain how a glow discharge optical emission spectroscopy works. Actually, we create a glow discharge plasma in the chamber between two electrodes, the anode and cathode, and the sample stays in between these two electrodes. This chamber is filled with reduced pressure argon gas. So when we start the plasma, the argon atoms will be excited and they move super fast. These super fast moving argon atoms collide with the surface of sample and eject material from the surface. We call this phenomena sputtering. A sputtered material will be excited in the plasma and emit light. The light will go through the lens into the optical system. Inside the optical system, we disperse the light into the original wavelengths and detect each wavelength individually. Each wavelength represents an atom, and the intensity of light represents the concentration of that atom. At the end of the analysis, you will see a crater on the surface of your sample, the same as the one you see here in the middle of the screen, and the results will be reported as a chart. The x-axis is the intensity of light, the y-axis is the time, which represents the depth of the crater. And each line, each color represent an element. So you can see how each element change in depth of the sample. So you can follow the evolution of your sample. Now, these are some examples of applications in which GD-OES can be used. This is just a few examples of a long list, and you can see using GD-OES in lithium-ion batteries is very common. It's a common application, but there are more for this instrument and this technique. Now, why we should use why we should use GD-OES for analytical measurement. As you can see, GD-OES can detect all elements in the periodic table from hydrogen all the way to uranium. It includes all light metals like lithium, light elements like carbon, nitrogen, oxygen, hydrogen, even the isotopes like deuterium and fluorine. So with this wide range of detection, GD-OES is a very powerful tool for analytical technique. Also, using GD-OES is very easy. There is no need for sample prep, and it doesn't work under high vacuum. So using GD-OES is easy and measurement is fast because you can measure surface from a few nanometer all the way to 150 microns in minutes. So it is fast compared to other techniques. Also, GD technique can give you qualitative and quantitative data if calibrated using some standards. And last but not least, the detection limit for GD-OES is ppm, in range of ppm, and it can go up to 100%. So GD-OES not only can detect very low concentration, but also at the same time can detect very high concentration up to 100%. So with that being said, I will go into application of GD-OES for lithium-ion battery measurement. So this is an example of a good cathode, a non-damaged cathode, which has been analyzed with GD-OES, and you can see the graph. Now, we did the same test on the same type of cathode, but partially damaged. So you can see the changes. In the beginning, at the surface, you can see some aluminum and barium, which is which happened after the damage. And after that, you can see a fully damaged cathode, which has more aluminum and barium at the beginning, at the surface. So with GD, we can detect the problem, and then we can identify the source of problem based on the type of elements which are causing this issue. We can actually um, predict what is happening inside the battery and why this is happening. So the first step is to understand the problem, and then we can identify the source of the problem, and we can fix the issue. Okay. For some reason, my computer is slow. Okay. So this is the second test, which has been done on anode. So this is a measurement on an anode. On the right, you see the full spectrum. You see the full profile from the extreme surface all the way to collector. And you see here, we were able to sputter almost 100, almost 100 micron in like 10 minutes. So this explains how fast this technique can be. And then if you focus on the extreme surface, which you can see on the left side of the screen, you see a spike of lithium in the beginning, which means lithium has been migrated, has been shifted from the solid electrolyte interface. And again, first we identified the problem, and then we found the reason for this. So next example is another cathode, which again, this cathode is not damaged, is not as bad as the one you saw in the previous slide, but still it is used. This profile shows a cathode after several charge and recharging cycles. So as you can see, again, at the surface, we have some spike of fluorine, and this fluorine is migrating from the separator. So again, by glow discharge optical emission spectroscopy, we can identify the problem, and then we can find the source of problem. Now, for many lithium-ion battery samples, air or humidity is enemy. So if we use the sample in regular environment, the sample will be damaged. With that being said, actually at Horiba, we have a patented device which can hold the sample in an inert environment and avoid any air or humidity contact during the transfer or measurement. And we call this device lithium bell because originally it has been designed to protect lithium ion battery electrodes during the measurement. Now, if I give you an example of how this device can help us, for example, you can prepare your sample inside the glove box and then put it inside the lithium bell and transfer it to the instrument and do the measurement. And then you can see the difference in the results. So on the right side, you see the results of the same sample without using lithium bell. The sample was exposed into air, and you can see the amount of oxygen and the penetration of oxygen in deeper layers of the sample. On the left side, you see the profile for the same sample, but in the lithium belt without being exposed to air. So this is another tool which we have and can help with special samples which are sensitive to air. This is another feature which is patented for HORIBA, and with this feature, which we call it UFS, stands for ultra fast sputtering, we can go up to 100, 110 microns in 10, 20 minutes. This technique not only makes our measurement faster, but also makes our crater better. So on the bottom left side of the screen, you see two different spots of different sputtering of the same sample. One without UFS on the left and one with UFS on the right. First of all, on the right spot, you can see we went through the whole cathode all the way to the collector, which is copper, and you can see the copper. On the left side, without UFS, we were not able to go all the way through the electrode. And not only this, but also the shape of crater. You see how good is the shape of crater when we use the UFS technique. So these are some examples of applications of GD-OES for lithium-ion battery. The next feature, which is available for HORIBA GD Profiler 2, is the Pulse RF system. With the Pulse RF system, we control the sputtering rate while we keep our intensity of light maximum, which means if your sample is sensitive to the plasma, to the temperature, to sputtering, we can reduce the damaging effect of plasma while keeping the intensity of light the same and do the analysis as it should. So on the left side on the screen, you see the depth profile of a crater without pulsed RF, and on the right side, you see the same sample with pulsed RF sputtering. And you see the difference in lithium. The red line is the lithium. On the left side, the lithium starts from low and it goes high gradually. But on the right side, the lithium level is steady from the beginning. So this is another feature which is patented for HORIBA GD Profiler. This one I skipped. And finally, the GD technique is both qualitative and quantitative. So with that being said, here on the right bottom table, you see the quantitative data for both cathode and anode. The top row is cathode and the lower row is anode. And we were able to quantify the, uh, the composition of the anode and the cathode in lithium-ion battery electrodes. Now, because GD Profiler 2 is one of a few techniques which can detect hydrogen, we are able to use this technique in fuel cell industry. As you can see here, these are two different profile for PEM for PEM of a fuel cell, and we monitor the diffusion of hydrogen in the PM. So with that being said, actually we can compare different type of PMs. We can compare the diffusion rate of hydrogen in different type of material, and uh, and not only uh, characterize the material, but also do some quality control in this type of material. So before I go to conclusion, I want to show you some other uses of GD in energy sector. Actually, not only in lithium-ion battery and fuel cell, but also in nuclear facilities and nuclear energy plant. GD-OES can help. As you can see here on the right side of the screen, this is a depth profile which shows the penetration of hydrogen and deuterium in reactor body. So GD Profiler 2 can be used for molten salt coolant system. It can be used for reactor material. It can be used for different parts of this sort of industries. And finally, I can conclude that GD-OES is an elemental depth profiling technique which complement other depth profile techniques such as XRF, SEM, XPS, or even Raman spectroscopy, which gives us some molecular information and data about the material. So with this, I will conclude my presentation and I will hand it over to my colleague, Sergey. Sergey, it's all yours.
Thank you, Kayvon. This is like a situation when we can really complete the two technique and several technique actually in an instance. And we're going to switch our gears and we're going a little bit about this basics of X-ray fluorescence. So X-ray fluorescence technology, you could probably know this because you know this EDS, but there is a two version of the EDS fluorescence technology. One of them EDS, which is electron beam excited, and another one ED-XRF, when we excite this material by the X-ray beam. Both of them generate the same fluorescence X-ray. So once this primary excitation beam hits the atom, it ejects the electron from the core and creates a vacancy. So electron from the higher shells is jumping to the vacancy and creates the characteristics waves. And this is because the energy of each level, KLM, are unique for the elements. We have unique spectrum, unique fingerprint for any elements. Later, you can see some kind of the characteristic of that, can talk about the K line, L line. So what this means, so in characteristic X-ray names, so the names of the line is according to Shelbyville field. When I'm saying about the K line, it means something can fall down to the K line, and the lane line is the L line. And number of shell changing by electron, if it's one shell is changing, for example, from L to K, it will be alpha line. If it's two shells, it will be beta line. So now, going to a little bit further, this technique is, Now, and this is, Horiba makes several instruments for the X-ray fluorescence. One of this is MESO 50. It's a relatively portable instrument. It has a palladium tube. It has a generator which is up to the 10 watts and has a CCD detector. It has a software controlled 3 spot size 1.2 millimeters, 3 millimeters, and 7 millimeters. It has this integrated 4 primary filter and may detect the elements from aluminum till americium. Another, it's a microscope. It's also XRF system. It's a real microscope. You can see the microscope, and I'll show you later some pictures. So it has this rhodium tube. It has this 50-watt air-cooled generator. It has a silicon drift detector, 60 square millimeters. It has a software controller different, like up to the 4 spot sizes. And the range of spot sizes is very good. It's from the 10 microns to 1.2. As you can see here, 1.2 is the largest one to the microscope, and 1.2 is the smaller for the MESO 50. So we have very nice overlapping between the different instruments. And 10 micron spots, so 15 micron spots is going to be very close to the ACM. So we covering the bridge between the ACM and the bulk XRF. It has a primary 5 filters, allowed you to do very low concentration profile for the some elements, and each filter dedicated for specific energy range. Besides of that, instrument equipped with a full vacuum capability, partial vacuum capability, ambient condition, hidden purge. And we can detect elements starting from the boron till americium. So I want you to point out this is a boron, it's the lightest element. It's only our instrument can detect it. There is no other instrument on the market which can do detect the boron. So also we can offer to our customer inline XRF. It's for the platinum, iridium, and some other electrode. And this is absolutely different technology, and we can put it several units XV100 on a belt and do the measurements and cover a very large area. And low detection limit for the it's like several milligram per square millimeters, and for the 10 milligram for quantification. Specifically designed for the platinum and iridium. However, it can be adjusted for the other element like nickel, manganese, and cobalt. So it can be used either for the fuel cells or for the lithium batteries. Now here is how the microscope looks like. So at a microscope we have the X-ray generator, which is putting the X-ray tube. It's a microspot generator through the filter wheel. This filter wheel can be either open or it has several filters. After that, the X-ray going through the X-ray optics. We're using different X-ray optic depending on the situation. It may be the polycapillary optics, maybe monocapillary optics. So you have the really microscope objective here, which allows you to see the sample with a very high resolution. And after that, this X-ray hits the sample. It creates the XRF signal. Besides of that, the X-ray can penetrate through the sample, and we have the X-ray transmission detector. This is feature like X-ray transmission detector is unique feature for our instrument. No one in the market can offer you X-ray transmission image. The XRF signal detected by the detectors are going to the spectrometer, and they can see the spectrum. Here's this example of the spectrum of the NMC, and you can see how well resolved it lines because we have the very sensitive high resolution energy silicon drift detector. Now let's look what we have more in this case and why we need the different ambient conditions. So this is an example just showing why we need the several conditions for the measurements. So if you're doing the full vacuum, as you can see here in the blue line, you can see very pronounce it sodium, magnesium, aluminum, and silica. If you have the partial vacuum, the intensity getting slightly lower, and ambient condition in the air, we have probably very low detection for the sodium, magnesium, aluminum. So all light elements supposed to be detected either in the vacuum or partial vacuum, the helium purge, because the high energy elements is not very sensitive to the vacuum condition. But if you have some sample which contain light elements, it's best way to use this our technology, because we offering again four different options: full vacuum, helium purge, partial vacuum, and ambient condition. Partial vacuum is very useful as well, as you can do the measurements in the solution or biological cell that can be damaged by the vacuum. You also can apply this helium purge to do the measurements for the high sensitivity for the light elements. Now, let's look for the nickel, cobalt, manganese. So what we can do here in XRF, we can actually check the composition. And in this case, we can differentiate some kind of the composition profile for different vendors if you really want to see or reproduce a specific composition profile. Here is the composition profile for NCM 111 for 3 different vendors. As you can see here, there are certain differences in the concentration profile, which may be or may not be important. However, we always have to check it and see if it's like really going well or not. And so this material can be used as a QC tool. And this is comparison of the NMC 111 and 811, how the spectrum looks like. And then we can see differently a composition profile. As you can see, the nickel is 811 is slightly higher for this particular sample compared with the composition which is supposed to be 811. Now, if you're doing the sample 1, we can do the mapping. It's a very important feature in any kind of the microscopy and XRF system, because we can see the distribution of the elements over the certain area. So on this example, I'll show you it's a distribution of nickel, cobalt, and manganese, and along with the transmission image. As you can see here for this sample, there are certain kind of the things which will be very important for us, like roughness of the sample or intensity profile over the map. Like that entire spectrum, we can detect other elements which may be present in the sample. In this case, it's see the presence of the sulfur, which is only in the 2 spots, which may be contamination. In this case, you can use this technology for, let's say, industrial forensics. So you can investigate this, for example, cells which are not really good, and see what the cause route for the not proper usage or some contamination. This example, another sample 2. So what we can go here, and you can see exactly as the same, like transmission image, which shows some distribution of density profile for this particular electrode, and nickel, cobalt, and manganese here. And then we can see, well, from the spectra, you can see aluminum in one spot and also the sulfur. So this is a part is a contamination of the material, which can create some problem for the electrode performance. Now we can go to switch our gear to separator, which is very important, and this is actual separator, and we can see some kind of, when you do the mapping, as a bright spot which correspond to the copper. And this is a copper may cause some problem in the assembly, electrode assembly. So Horiba is offering you a special transfer vessel, which allowed you to put the sample in the transfer vessel in your glove box, bring it to the instrument, make it a vacuum inside of the instrument, and remotely open the vessel and do analysis of the instrument without this air contamination or air reaction with lithium battery or other some kind of material. And in this case, XGT 9000 is the best tool to do such kind of the glove box instrument measurements and you not really contact with the air or oxygen or water. So next, switching the gear to the fuel cells, and this is a platinum sample, and you can see here this distribution of the platinum. There is a certain kind of the roughness of the platinum, and transmission image actually show exactly the same situation. That you have the rough platinum samples. It may be also connected with the performance of the material. So in this case, if you're looking for the second sample, which we can make it, it's much more smoother. So distribution of the platinum is more uniform, and in this case we can see what is the performance of the one sample or another one. So in this case, mapping of the sample is very important, and besides of that, we can quantify platinum content in all the samples. Next example is how we can do quantification. So we do have different technology to do the quantification of the platinum, which integrated in our software. So one of them, we can see the standard, and this is a XRF spectra of the platinum standards, contained standards. And here is a picture of the samples on in the instrument. So we do have software which allows you to assign each kind of the particular sample and run it without your attention and say, okay, I want to run it 6 samples in one shot, and it will do the 6 different measurements of the mapping. Now here is how it maps looks like, and you can see this is a blank, this is a sample with different composition, and number 5 is shown distribution of the platinum of the sample with the highest concentration. What we're going to do now, we can create the calibration curve. So we can create the calibration curve, and we can see the very important, we have the samples are quite linear, and we have the R square is 999. It's very good, so we have to do the good quantification. However, if we apply this calibration curve, we don't know what is the error. How much error if we apply calibration curve, it happens with the sample. So the next technology we can offer you, taking the same spectrum and doing the same exact things, but we apply partial least square analysis. So PLS modeling gives you some exactly very well done R square like 0.999. However, this technology allowed you to estimate what is the error in our calibration, and if we apply this particular calibration curve to this sample, what would be our error estimation calculation. Here is an example, and you can see I took the same samples which I measured at 107, and my predicted value for this particular model is 0.4142, and with the 301 I have much better 0.99. So what does it means? We have quite a big error here, and we need to understand how we can handle. We offering to our customers slightly different approach, because we always using this hyperspectral image, so we get an entire spectrum range. And now instead to using the area or intensity, we're using the each point, it's in spectra, and then we can create the calibration curve. Now we have the R square value as well, very high. It's the same like in 2 previous cases, 999, but we can estimate what should be our error. So when we're doing and apply this model based on the spectrum, not on the area, not on the intensity, on the spectrum, we can get very good result in quantification, showing that we almost the same number we apply. The reason for this is because in this calibration curve we have much more points in the calculation compared with just the one numbers. So this is very important part, and we can using different technology in quantification, whatever you want to do it, and you can check it whatever you want to simple and more fitted for you. Now let me switch it a little bit for the Raman spectroscopy. Raman spectroscopy is molecular spectroscopy. So we're talking about the GD and XRF. This is elemental analysis. We're looking for each element. And the Raman spectroscopy is looking for the molecular vibrations. So when the laser is hitting these molecules, there is several processes which can be done. First of them, it's Rayleigh scattering. So light is scattering from the molecules without changing this frequency. And there is a stock scattering when the molecules absorb the some light and emitted the light which has a less energy, stock side. But it's also possible to light emit with the energy which is slightly higher on vibration of the anti-stock light. Now, if we can look for this effect, so Raman spectroscopy, it observes the energy changes as excited molecular vibration. The unit in the unit and relative energy, it's a relative energy. We're talking only about the energy. This is like lambda of laser divided by minus lambda of peak, but it's inverse. Now, why are we doing this one? So I take a simple example. It's a silicon band and 520 wave numbers, which is energy 0.64 at 6 millielectron volt. If I'm using laser 405, my difference between this laser line and silicon line will be 8.72 nanometers. If I use 532, it will be 15.15. If I take the 633, it will be 21.6. So it's very difficult to see it. However, if I present it as an energy scale or wavelength, Raman shift scale, it will be the same. So what it means in a Raman spectroscopy, your peak position in general doesn't depend on the excitation. You can choose whatever laser you better to prefer or working better for you. Now, looking for instrumentation for the company. So Hariba make it several instruments which is fitted for the different purposes, and you can choose whatever you want to have. One of them is Labram Odyssey. It's a research grade instrument. It can be equipped up to the 3 different detectors. It can accommodate 7.5 lasers and working for the condition from the deep UV, like 200 nanometers up to this 2000 nanometers. Another one is in the middle is Labram Soleil. It's an imaging system. It's a very nice spectrometer working from the 300 nanometers UV up to the 1700 nanometer in EIR. And another one which is open compartment, it's Explorer Plus, which works on with visible laser like 532, 638, and 785. Besides of that, all these instruments working on the same software platform. It means you have the same feature. For example, I show here examples like View Sharp. So you have this software can allow you to make it Z-stack and make it entire sample very flat. You can use a multi-point analysis. You can do the multivariate analysis. And you also can work with a different cells, electrochemical cells. Here an example how the cells is located under the Explorer Plus. And we also can offer several versions of the electrochemical cells to study that electrochemical reaction in situ. So here's an example why Raman spectroscopy can do it. So very often the composition may be the same, however, the chemistry will be slightly different. And this example of the 2 different NMC111 from different vendors. And you can see materials look slightly different optically, but the spectra also looks slightly differently. But it also can be used to do QC on the materials, which is provided by the different vendors. Now, if you're looking for the different differences in the 111 and 811, you can see the spectra is remarkably different. So main peak on the 8111 is 594, but 811 is 550. So in this case, you can really differentiate the 2 materials or conversion one materials to another one. Now we're going to the little bit in degradation of cathode during the charge-discharge cycle. This is very important things which is you always study. Here is like we have some kind of this is a picture of the mapped area of the electrode, and you can see the spectrum of fresh electrode. So what happens in this case, you can see because the NMC electrode has a usually layer structure, and the lithium atom can be going through quite easy, and we see the distribution of E to G band. So E band is like very low, but still exists. So there is a certain defect in the structure, but it's still a band. It's dominated. Now, when we do the cycling, we see the capacity attention ratio. So capacity of battery go down. So let me see what happens if we can apply the Raman spectroscopy and what happens with the spectrum. So spectrum becomes like really quite different. This is the reason why it's like different, because structure of the material has changed. So due to this charge-discharge process, layer structure converted either with spinel or rock salt structure. And this gives you like kind of the voids and trap this lithium atom inside and not allow them to move in and out. So, and here you can see this ratio between A1 to EG ratio, and you can see the number is significantly below. This is the reason how you can use this Raman spectroscopy to detect different degradations or different changes in the electrode due to the charge-discharge process. And because you can put it in electrochemical cells, you can definitely can see in time of the charge-discharge what happens with the electron. Now here another, because they have the carbon-based anodes, and the carbon has a different form. Here is slides that show what kind of form of carbon we would expect. And the G to D ratio, it's actually a measure of disorder of the carbon. Now, what we can do is that we also can do the imaging of the electrode or mapping of electron. Here is a picture of electrode. So, and then it's a spectrum of different features. We can apply the multivariance analysis, which is integrated in our software, and see the distribution of all these species here. And then we can overlay an optical image and monitor which feature is correspond to which kind of part of optical image. And it's allowed you to see what will be, again, the degradation of electrode, or how the electrodes evolve in the sense of the charging-discharging process as well. For carbon-based analysis, we have the very good feature which is called the application in our software lab spec. It's Q-Carbon. It's automated carbon analysis application. So we loaded the map, which I have here, and in one click you can do this fitting parameters, you can do ratio, you can statistics, and you can do many things that can be done with data. And you can assign up to the 10 different peak of the carbon. What I showed you before, it was like 3 different species, but if you have more of them, you can include in a Q-Carbon application. And in this case, you can analyze it much in a different manner. Now, is there is a bridge between the molecular structure and elemental structure, and this is a couple more slides is showing you, as remember the platinum-coated sample 1. So if I do the analysis using the Raman, because the carbon is always present in these materials, I see this such kind of distribution. And you see the broad distribution of the particle size. And I can do that again, everything in using Q-Carbon. Now we can look for the platinum-coated sample, and you see the rough surface. So there's a certain correlation between the carbon distribution and a platinum distribution as well. And if I apply this technology to this another sample, you can see very narrow distribution of particles, and and the map to DG ratio looks very good in sense of the distribution. And then if I look it up for the platinum, you see the platinum coating and transmission image show relatively smooth distribution and shows a very good quality of the materials. On this last slide, I'm finished this, and I would like to thank you for attending this webinar. And I will take any question if you have it.
All right. Thank you both very much for the presentation. We'll now jump into the Q&A portion. So if you have not sent in your question yet, please do so now. And we'll start working through and try to get to as many as we can. So the first question I see here is, how deep can GD sputter, and what is the depth resolution?
Okay. All right. So I guess I actually answered this question during the presentation, but we can go up down to 150 micron inside the sample. So the depth is maximum 150 micron, and we can identify different layers within nanometer scale. So the depth resolution is like 5.4 nanometer, and the maximum deep we can go is 150 micron.
All right, thank you very much. Let's go with how long does it take for GD to analyze the lithium battery cathode?
Okay, so it depends on the thickness of the cathode and, of course, the composition. But in general, you can sputter the whole cathode and go through the cathode all the way to collector in 10 to 15 minutes, depending on the thickness of the electrode and the type of material. But it is within this range of timing, like between 10 to 15 minutes.
All right, thank you very much. Let's see here. The next one I see, is it possible to do a full spectrum analysis with GD?
Yes, thank you. This is a very good question. Well, actually, our instrument can be equipped with a monochromator, which can scan the entire spectrum from 120 nanometer all the way to 800 nanometer. With this feature, you can do a full scan of your sample for all elements in this range, and then you can identify uh, the elements which emit light in the spectrum, and basically you can identify any element inside your sample with this full spectrum. But the most application for this feature is quality control, because the spectrum of each sample is like a fingerprint for human. So if you take the full spectrum of a good sample and then take a full spectrum um, of your sample which is in question, then you can superimpose these two spectrum and see the differences and see if there is any difference in intensities, or even some extra lines which doesn't exist in one or exist in another. So it's kind of very quick and reliable quality control tool.
All right, thank you. We've got time for probably 2 or 3 more questions. Does the GD operate under a vacuum or low pressure?
Yes, actually we apply vacuum, but it is inside the chamber, and it is not very low vacuum. It's a regular vacuum, like 400, 600 Pascal.
Okay. What is UFS?
Okay, so UFS stands for ultra fast sputtering. This technique, which is patented for HORIBA, uh, originally developed for lithium-ion battery cathodes, but it applies to any organic material, polymers, coatings like paints, and any high carbon content material like DLC. So this technique actually helps us to eliminate the carbon buildup inside the chamber, and at the same time expedite the sputtering rate.
All right, thank you very much. I think we can squeeze a couple more in. Are partial vacuum and HE purge standard, or are they options?
Partial vacuum is a standard, and helium purge is option.
Okay. Is the chemometric package integrated into the software?
One part is integrated in the software, but for full chemometric package is not integrated, is an option as well.
Okay. Let's see here. Probably try to squeeze a couple more. What is the lifetime of an X-ray generator?
The warranty is like 2,000 hours, but usually it stays much longer.
Okay. What objectives would you recommend for measuring in an electrochemical cell?
Usually working distance supposed to be like 10 millimeters, so it's a 50x with a high numerical aperture objective for 60x, depending on your particular cell.
All right. Let's see here. What is the smallest shift of the Raman band that can be detected?
Well, it depends on the material, but we can put 0.1 wave numbers.
Right, and we'll end on, does Orbia offer technology to reduce laser power at a sample or distribute power during measurements to avoid thermo or photo-induced damages?
Yes, we do have two different technology can be integrated in our system, which allows you to rastering beam, and this is really drastically reduces power density as a sample. Yes.
All right. I think we got time for one more. How do you separate thermo and photo damage when high power is used?
So this is some kind of the situation when we can use this rastering beam and see if its spectrum is shifted or not. And in this case, we can using this comparison. So for the straight light, we see the certain kind of the shift, and when we can distribute the power on the materials, we can see a shift, or we cannot see the shift. In this case, we can separate a thermal effect, and if there is a photo effect, you also can see it definitely, but it's quite little bit more difficult to separate, but it's also possible using this different power measurements at the sample, so we can control the power measurements at the sample in the software as well.
All right. Well, I just want to thank both of our presenters for your time and important research. I'd like to thank LabRoots and our sponsor, Horiba, for underwriting today's educational webcast. Before we go, I'd like to thank the audience for joining us and all your questions. Questions that we didn't have time for today and those that get submitted during that on-demand period will be submitted to our speakers. This webcast will be available on demand, and LabRoots will alert you via email when that's available for replay. We do encourage you to share that email with your colleagues who may have missed today's live event. So until next time, I just want to thank everyone once again, and goodbye.